Okay, let's get started. So I've had the good fortune of speaking at the QE2 Centre a number of times over the last decade. I am that old. And I have come to the conclusion that this is by far and away my favourite room. The reason this is my favourite room is that the audience has to really want it, right? Because on the ground floor, it's the closest rooms to the pub. You've got the rooms on floor 3, which is like, well, I've had some food and I can't be bothered to get anywhere else. So I can't just roll into those other rooms. But for this room, you've really got to want it. You've got to go through staircases and lifts and fight through the halls and not be distracted by the beanbags downstairs, which is normally where I hide when these particular events are on. So thank you so much. You are my kind of people. So thank you indeed for coming along. We're going to be talking today about, is the definition of insanity what we think it is? And really a discussion about how we can, or some fundamental things that we can do to make our distributed systems more resilient, more robust. And these really are what I think are some foundational technical things that you should be doing if you are building a distributed system and you want it to have some semblance of resiliency and robustness. This talk is partly the outcome of a book I've been working on for about a year now called What's This? And it's in early access now. You can get more information about it over at my website. There's about 5 chapters up at the moment, including the chapters that I'm talking about today. The full book should be out towards the end of the year. But we are going to be focusing today on 3 core ideas that I talk about in this book: timeouts, retries, and idempotency. So timeouts, right? Timeouts, knowing when to give up on something. Retries, knowing when to try again. And idempotency, which is knowing when retrying again is actually going to be safe. We'll also maybe along the way be discussing this particular quote to see if either A, it is valid, and B, whether or not it's what we think it is. Let's start out though by talking about the context in which we are operating. Don't worry, there will be slide downloads at the end. I have QR codes for you. Let's talk about the world in which we are operating, which is in the world of distributed systems. It's pretty worth explaining what a distributed system is, because they're actually quite fundamental and they're everywhere. And even if you don't think you're building one, you probably are. Technically speaking, a distributed system is one where 2 or more computers communicate with each other via networks. The more distributed these systems become, generally the headaches also increase. But this is fundamentally what a distributed system is. So here I've got 2 computers and they are communicating with each other via a network. Sometimes you're doing that quite directly. You're opening up network connections. You're sending bits and bytes yourself. Sometimes you're doing it indirectly, maybe via programming abstraction. You're using gRPC, for example. Still using a network. Maybe you're using a message broker. Maybe you're using a file system to communicate between computers. It's always networks underneath all of that. Saying a distributed system is 2 or more computers connected by a network is a very dry description of it, because it doesn't really speak to the sort of horror, pain, and suffering that comes from anything related to networks, and indeed computers, and indeed people, and even rabbits, which we'll get to a little bit later on. This is actually my favourite definition of a distributed system, which comes from computing pioneer Leslie Lamport. A distributed system is one in which the failure of a computer that you didn't even know existed can cause your own computer to be unusable. Right? Things fall apart. And if you really want things to fall apart quickly, use a distributed system. Things do tend to collapse quite a bit. Now, I'm not going to, in this talk, try and talk about all the ways in which we can stop these systems falling apart, but I am at least going to deal with some of the fundamentals. And behind it all, there are these nagging challenges that we have to deal with. Now, there are lots of different ways of framing the challenges of distributed systems, such as the fallacies of distributed computing, which is one of my own personal favorites. I think Kevlin's going to be talking about that a little bit later on. But I've realized through my own work and research and looking into things like cap theory and harvest and yield and all this stuff, that fundamentally all of the challenges of distributed systems from a developer point of view come down to just 2 things. Firstly, you cannot beam information instantaneously between 2 points. I know that theoretically this is doable with something called quantum entanglement, where you can mirror the electron spin states, and that is theoretically doable, but, and this is very important, that is not a networking protocol. In addition, I believe it only works for read states. So it takes time, and how long it takes is only partly under your control. The second golden constraint, if you will, of distributed systems is sometimes you can't reach the thing you want to talk to. This is it. This is everything. Now, the logical conclusion of all of these things is lots of complexity. However, I always find that when you find yourself lost in something weird going on, having these rules at the back of your mind and realizing that you only have partial control over these two factors is important. You do have some control. You do not, and never will do, have total control over both these things. And once you accept that, I find that most of the complexities of distributed systems just end up actually being common sense, hidden behind flowery languages and the vague marketing of various vendors. We are going to start by talking about timeouts. Timeouts are basic, they are fundamental. And they speak very much to the fact that you can't beam information instantaneously between 2 points, and that sometimes the thing you want to talk to isn't there, therefore we need timeouts. So what is a timeout? A timeout is a threshold after which we're going to give up. We tried doing something, and rather than waiting, we're going to give up. So we're specifying a threshold, and once that threshold is reached, we give up. So in this situation here, I want to go make a payment. I say, can you make a payment? And I don't get a response. And at a certain point, I go, right, I'm done. It's probably worth just exploring briefly why we even have timeouts. Right? Why not just wait forever? Because you don't want that. Let's talk about why. Well, firstly, we just have the problem of computing resources. If one computer is waiting for another computer to do something, you are tying up computing resources. Yes, even if you are using some non-blocking extension and think you're all asynchronous, there are computing resources tied up if fundamentally your computer is maintaining a network connection, waiting for something to happen, right? So if you're waiting forever, computing resources do get tied up. You can mitigate this somewhat. Right? Non-blocking I/O can help, for example, but it can't eliminate that. So if I'm waiting forever and new work keeps arriving, I've got more proportion of my computing resources, both on the client and server, are now potentially contended doing stuff. And this is an issue because as you start to use up those computing resources, things start to go wrong. Systems start to get slower, which can make timeouts worse. Systems can collapse, and things get problematic. So we don't want to just wait forever because resources are tied up. Resource contention is a problem. We also have the issue, of course, is that sometimes we have these irritating things in our systems called human beings. And human beings are waiting for things. They are not going to wait forever. And in fact, if you make them wait too long, they might not do what you want them to do. I'll give you a slight case study which helped. This is my first sort of indoctrination into understanding that getting timeouts right was important. This would have been 2008, I want to say. And I was helping sort of re-architect a site for selling, amongst other things, used cars, new cars, motorbikes, and things like that. It's a UK-based company. And we had lots of old websites for selling different types of products. And we were bringing them all together under one system because there's actually a lot of commonality between these different products. Used cars happen to be the biggest market. So here we are. We've got our application, which was called Sauron, for reasons I hopefully don't have to go into. But this was basically an application where we were gradually kind of absorbing the functionality of all these old websites in this particular system. And normally, at peak, each of our nodes would be running between 30 to 60 concurrent requests, which is not much at all. These machines had loads of excess capacity. They could have handled more requests they wanted to. But even at peak, this is pretty good. Now, above our app, we were taking in about 8,000 requests per second, which was pretty much cached entirely within using a system called Squid that sat in front of all of this. So with a lot of load coming in, these were basic cache misses. Load quite small. However, something went wrong. Our site started behaving quite slowly and then fell over in a very quick, short space of time. And we were seeing a spike from these nodes normally handling between 30 to 60 concurrent requests to handling over 800 concurrent requests per machine. And this is with a Java runtime where one connection equals one operating system thread. So now all of these machines are now trying to schedule and prioritize 800 plus threads. So this was excellent hardware, by the way. It wasn't that excellent. So net result was all of those threads blocked, waiting on the machines. That caused complete CPU saturation, I/O saturation, the whole system ground to a halt. It went from everything being fine to everything not being fine in about half an hour. Luckily, it happened during the day, so we were all caffeinated and we could deal with it properly, right? It turned out there was an application further downstream that was causing all the issues. One of our websites was behaving in the worst way anything can behave in a distributed system, which is it was initially acknowledging a request and then doing nothing. So you could open the connection, you could send the request, and it would just go. And it would do that forever. And it was completely and utterly wedged in a way we'd never seen before. Now, we actually restarted the Caravan application, and it was fine again, and obviously we had to work out the fix. But that failing should not have caused the whole system to crash. It turned out it was largely, not entirely, due to timeouts. When a request came into our application and said, I want to see some caravans, we would take that request, we'd go get a worker out of the connection pool, and then use that to establish the HTTP connection to the Caravan website. This is standard connection pooling. It works in the same way in .NET. It works same, if you use Poly, the built-in stuff in .NET, same thing in Java. Connection pools are ways of limiting the number of outbound bank connections you have. You will be doing this even if you don't realize it. So you pick up a worker, and then you use that worker to make the call. And so that was how you'd establish the call out to the Caravan site. So it was taking a long time to respond. So a lot of the workers were now tied up waiting for the Caravan site to respond. And it was a problem because while we were blocked waiting, the users who had gone to look at the caravans got bored and they had refreshed their browser. That's a problem because the original request they put into our system is still there. They have refreshed their browser and then it didn't work. So what did they do again? They really wanted to see that caravan. They hit refresh again. And when that didn't work, they kept refreshing. Even more annoyingly, these other sites were working perfectly fine, but the connection pool was shared, and so no requests were getting through to those apps either. Not great. The biggest issue, and there were others, was that we weren't timing out quickly enough. When you got a worker out of the connection pool, the default behavior of this particular connection pool, the Jakarta Commons one, was 30 seconds. So you'd wait 30 seconds before giving up. Even in 2008, we knew that our users would wait 10 seconds or less. Right? They're not going to wait 30 seconds. So that was way too aggressive. Even worse, when you went to the connection pool and said, can I have a worker, please? There was a timeout specified for that, and it was set to -1, which means it would wait forever. And that's where the fundamental problem was. This was default behavior, by the way. These two numbers basically took the whole system down. The connection pool was exhausted, so nothing else could happen. All those requests coming in were blocked, waiting on the connection pool. And even if someone hit refresh on their browser, those connections didn't go away. Now, there's a lot more we did with this system other than fixing the timeouts. I can do another talk where we talk about bulkheading and circuit breakers and rate limiting and load shedding and all those other things, but we're here to talk about the timeouts. Getting timeouts right is kind of hard. If you get a timeout too short, you might give up on something that may otherwise have worked, in which case that's just wasted effort. And it could be even worse if that then causes you to then retry. If you wait too long, you can increase the resource contention to the point where the system becomes potentially unstable. And so trying to find that balance is kind of really tricky. So if you're not sure right now if you've got the right timeouts, what do you do? Well, one of the most important things to do is to understand what is normal system behavior. When things are operating well, what do we normally expect in terms of how long things take? And ideally, you'd put this up on a histogram. So histograms are really fantastic ways of visualizing information, this type of information. What a histogram does is it's showing frequency. So as we go from left to right, we are seeing calls that took longer. So the calls over here took 250 milliseconds, and the calls down at the end took 10 milliseconds. We're going to assume that's going to be a cache hit to some sort. And so as we go up, that's the frequency. So you can start to get a sense of the shape of your response times. Histograms are very, very useful for seeing patterns. So we could say, look, we've got some weird outliers. Is that a problem? We'll come back to those a bit later on. And you might start saying, well, actually, look, the vast majority of our calls completed successfully around here. So you're already starting to have conversations about where you place these lines. Don't do averages. Averages are useless, absolutely useless for tuning these things. It's all about looking at the distribution and the shape. This is useful. So what is your current behavior? When things go well, where are these lines normally? That's a good starting point. If you don't have the ability to extract that information from your systems today, you can get that ability in there. The next piece is then to overlay user expectations. How long are your users going to wait? We were waiting 30 seconds. How long were our people actually going to wait for a page to load? Now, the annoying thing was we already had targets defined. We already knew that our render time at the browser was 4 seconds. And that was already something we were working towards. So we had a number in mind, and yet we had a timeout that was way more generous than that. The third thing you need to do is to make sure you can change your timeouts without changing code. And this is quite important. Partly because you're going to want to check your timeouts are right by doing some load testing and playing around with some numbers, but also because if things start going weirdly wrong in production, you want to be able to fix it. Now, we'll come back to a real-life story about why that's so important a bit later on. Fundamentally, though, timeout is all about us prioritizing the health of the system over the success of a given request. That's what we're trying to do here. In general, when you're looking at timeouts and we're thinking about system performance and behavior, what you normally want to be aiming for is a fairly consistent behavior, right? So we want, ideally, if you're thinking about, say, the response time of a service, you don't want a huge variation of how long that operation can take when it works successfully. You want kind of fairly consistent, understandable behavior. And the reason that's important is because how do you know something's gone wrong? If you've got a huge variability, if a call could take anywhere from a second to 10 minutes to behave successfully or return successfully, that makes it quite difficult for you to set things like timeouts or trigger alerts when thresholds are reached. Right? So this is another way of saying being inconsistently fast might actually be worse than being consistently slow for things that work. Right? So here's one histogram, and here's another. Now, the number of calls is exactly the same. The average response time is also exactly the same. However, the latency here is a much tighter bound. So you'll probably, in general, find it much easier with a sort of a more compressed latency histogram like this to reason about, is it behaving correctly? Is something going wrong? Is something going awry? But again, you can't even reason about that unless you can see these pictures. These can also help you understand what these things are. Right? These are what we often call tail latencies, otherwise known as sort of high percentile latencies. These are outliers. And when you have a large number of calls, there's always a chance you're going to get some outliers. These things just sort of happen sometimes. Sometimes they happen because you had a machine that was unhealthy. You had a bit of network congestion. A packet went down the wrong leg of the internet. It could be structural issues. I've had this before when we were hitting a machine that was still running off spinning platters rather than running off SSDs, for example, although we all thought the instances were the same. So the problem with tail latencies is partly they pull out our understanding about what is our normal successful response time bounds. That's one issue. So it's going to distort our view of the world. But the other bigger issue is these tend to be human beings. If these tail latencies result in human beings being unhappy, that's going to be an impact. Right? And tail latencies can get worse as you get more distributed. And so if you're looking at something like a microservice architecture, we tend to push towards being a bit more fine-grained. If you also have some tail latencies in there as well, you can find these problems start to magnify. So let's imagine we've got a scenario here where the chance of one of our calls effectively being a tail latency is 1 in 100. So 1 in 100 calls between these two services will spike for some reason. Now, if we take that same frequency, and now we do a fan-out call, and each of those fan-out calls has the same kind of probability, we see a drastic increase in how likely we are to be affected by a tail latency. So let's imagine a call comes into a service, which in turn does some parallel processing across 5 machines. if each of those also has that same frequency of tail latencies, the chance of our initial call being impacted by that tail latency goes from being 1 in 100 to 5 in 100. So you see a big increase in how likely you are to be affected by tail latencies from an end user point of view as you increase the parallelism. Mark Brooker, who's got some awesome stuff all about this, has done some visualizations of this. So these are basically latency histograms. And as he ramps up the number of calls being done in parallel, you start to see how tail latencies can really warp our kind of perception of how long, well, the reality of how long things take. So as place animations, the number of parallel calls are increasing. So these are the latencies which are affected by the tail latencies, and these are the ones that aren't. So as we go, we see a larger and larger increase. I don't know why the colors aren't coming through on that one. So just increasing the parallelism increases the chance that you're going to see that impact. It also, of course, gets worse with sequential calls as well. Right? The same problem starts to occur. I mean, this is bad anyway from an overall latency point of view when you have lots of serial calls because your end-to-end latency becomes a problem. And if you've got a large variability in latency for each of these individual calls, that sums up and you get an even larger distribution here. So, in this example, he's done a similar, this is another one from Mark Brooker, where, again, what we're seeing here is as he increases the number of serial calls, same probability for any individual call to be a tail latency, you start to see some really odd warping effects. So initially, it's pretty much the same, and then these are the tail latencies here. And so as we increase the number of serial calls, you start seeing this bigger and bigger shift to the right. I mean, lots of serial calls aren't good anyway. If you want to get into, I could do a whole talk on tail latencies. Don't have time to go into how they happen and why and how you fix them. But a good starting point would be the tail at scale, which is sort of talks about how you do things like request hedging. This is by Jeff Dean and Louise Barrasso. And also Mark Brooker's original writing on this stuff, which is really, really great. Both of these are highly recommended. So we've talked about timeouts. At a certain point, we have to give up. So if we're going to give up at a certain point, the question is, well, what do we do next? Well, this is when we get into retries and we start thinking about this quote. The definition of insanity is doing the same thing over and over again and expecting a different result. Is that actually insane? Because I would argue it's not, at least in the context of a distributed system. Because we know from a distributed system that sometimes you can't reach the thing you want to talk to. And there are a whole host of reasons that might cause the thing you want to talk to not being there that might actually be short-term issues, that might be ephemeral issues. Maybe you were loading a web page and somebody who's definitely not the Russian military cut a subsea cable. But it wasn't them, definitely wasn't them. All right, they were nowhere near it when it happened. And if I refresh the page, my traffic's going to get routed via one of the other links. We're quite fortunate in the UK where these things happen, we don't get affected. I have actually lived in places where when this does go, you do lose the internet. Right, but we're quite fortunate that we have lots of redundancy around these things. It still does have an impact. I worked in one place, I worked in Leicester, my first ever job, and I worked in it's an old industrial estate, and they basically reused ducting that was there for like pipes and things between the buildings to also run the network cables. I don't know if this is in the middle of the countryside in Leicestershire, and one thing in the countryside that loves channels underground, rabbits. And I've got a friend who actually keeps rabbits, has house rabbits, and the thing they love more than anything else in the world is insulation around cables. It's like crack cocaine for them. So basically, the rabbits moved in, and they just ate the network cable, right? You can't handle that in your code, right? You don't have, the only way you have control of that situation is if you want to go down late at night with a shotgun. It's not necessarily a very nice thing to do. These things occur, though. I mean, we know that things sometimes fail, and that's what we have load balancers. Well, it's one of the reasons we have load balancers, right? I make a call. That order instance has having an issue. Maybe it hits the machine that's just being restarted or just being done by the out-of-memory killer on Kubernetes or whatever else. So that had an issue. So that call, maybe I timed that call out, or maybe the call just failed. The connection didn't even establish in the first place. But that's okay, because if I retry, the load balancer may be able to route my call to a node which is actually working. And so we know this is what happens, and that's why we have load balancers, and that's why you also know that retrying makes sense. I'm sure lots of you, I mean, how many people here are using Poly in .NET? That's about half of you, right? I suspect you're using the retry policies in Poly, of which there's a lot, right? Because you know this is a thing. So if at first you don't succeed, it might be worth trying again. This is absolutely fine and sensible. How many retries? 1, 2, 50? Now, of course, if you've got a sense of the overarching timeout or how long your client is willing to wait, the number of retries that you're going to take into account has to take that into account as well, right? You've got the timeouts for each individual call, but they sum up. If you retry too much, you might actually overload a server. I make a call, I time it out. I make a call, I time it out. I make a call, I time it out. If you retry too often, remember, a lot of the time those computing resources might still be timed out, or might still be tied up until the server can process them, even if the client has given up. So therefore, we set a maximum number of retries because we don't want to overload our servers. Next, we have to consider delays between retries. This is a problem that hit Square. So Square had a large-scale outage, I think it was 2017. Multipass, which is their authentication system internally, basically got restarted, and it was trying to establish a connection with Redis to put out its information. And basically, Redis was quite heavily loaded. The clients, the Multipass clients, would do 500 retries, right, with no delay between those retries, and that was hard-coded. And so what happened was, Multipass just kept getting hammered, and people were restarting the clients to think, oh, that's going to fix it, and that just increased the load. Now, those values were in code, they were hard-coded. They fixed it, but now if you find a problem like that, your timeout is wrong, or you don't have the right delay, and it's in code, you've now got to go change code, recompile, probably retest, redeploy. If it's in a text file, you just go change the text file. So put your timeouts and these things in a text file, and yes, delays are sensible. So put your retry limits and all these things. Now, the retries get interesting. I'm sure most of you, if you're using something like Poly or Resilience4j in the Java world, you're probably using one of the default retry policies, which will give you a exponential or semi-exponential back-off between the retries. So in other words, rather than having a fixed cadence, we actually have a variable cadence between retries, and that's quite common. It's not the only thing you need to do, though. What you can get is when all the clients start to synchronize, is you can get like waves hitting a server causing problems. So in this scenario here, right, we've got the calls coming in, and we're hitting a threshold, which is kind of where the server's starting to creak a little bit. And so a portion of those calls above that threshold start getting timed out, right? So what happens is some of those calls time out, and so they're going to get retried. Because they all timed out around the same sort of time, if they've all got roughly the same delay, they're all going to retry in the same duration. So they all come back as a cluster. Right, so this green area here is this first retry. And of course, that's still pushing us over that threshold. So a portion of those time out, and the other new calls time out as well. And if we wait at the same period of time, you can start to see these things magnify. So if you have very set durations between the retries of clients, even if, by the way, those clients have exponential backoffs, and exponential backoffs cause problems for user-facing stuff anyway, we still have an issue. So the way we solve this is by adding jitter. So networking jitter is like a variation in latency, and we're basically inserting artificial jitter. The way we do that is that your clients will add a random amount of delay. So there might be a normal delay, we're going to wait 200 millis, and there'll be a plus or minus some random amount. And the idea here is that we're going to space out those calls. The idea here is that we smooth off these peaks and we bridge them out. So the same number of calls in this scenario here are now much more spaced out. We're trying to reduce the peaks we're hitting, and actually also reduce the troughs as well. So again, use a good connection library. They will have these values allowed. Poly absolutely lets you specify this stuff. There'll be some defaults in there, but now you at least know why they're there, and you might even want to be able to change them. If you can do some load testing and view your response times on a histogram like that, you've now able to go start making some tweaks and seeing what happens. But in general, like, one of these graphs is better than the other, same number of calls, and I definitely would want the one on the right. The last thing we're going to talk about is, in many ways, the trickiest aspect. A lot of what I've talked about so far are things that you can sort of retrofit into existing applications. right? Okay, I can go see where my connection pools are, make sure the timeouts are correct, because probably you're using things already that give you these capabilities. So you can go in, you can make the observations, you can start doing the tweaks. The next bit gets a little bit trickier. And this is asking the question, rather, is it safe to retry something? So here we've got an operation where the order service wants to send me some money. Very generous of the order service. I'd like to think it comes from one of you. You want to pay me £100. So you say, pay Sam £100, but you don't get a response. Now, you're desperate to give me money. I'm desperate to take your money. I'm buying a house. But you're so desperate, you didn't get a response. I really want to make sure Sam gets the money. But we've got a tricky problem now. Because from the point of view of the order service, if you don't get a response, there are kind of two equally likely possibilities. The first possibility is that the request to me to say, pay Sam £100, the first possibility is that that never got picked up or processed. So the first possibility is the request was not processed in the first place. And that's why you didn't get a response, because the request wasn't processed. So maybe the request got lost on the way. Maybe the server picked up that request, but maybe crashed before it could complete processing and perform the write. That's one possibility. There's a second possibility, and this is kind of where things start to get a bit iffy. The second possibility is you sent the request got processed, but the response didn't get to you. And again, this could happen because, for example, let's imagine in the payment server, I was going to send the response rather, and my server crashed before I could send the response. But I'd probably send the response after I've done the write. This is partly why people use transactional outboxes, right, to avoid this problem. But even with the transactional outbox, there's still things that could go wrong that meant that that response never gets back to me. It certainly could happen in, say, a case where we're just communicating over HTTP. There's lots of situations where that could happen. So from the point of view of the order service, it's possible the money got paid, and it's possible the money didn't get paid, and you don't know which is which. It's like inside this box, there's either a dead cat or an alive cat, and in either case, I want my £100, right? So what do you do? Now, if you say pay Sam £100 and you don't get a response, but it was actually paid, and then you say pay Sam £100 again, in this situation, from your point of view, you might have the undesirable situation that you've now actually paid me £200. To be really clear, I'm pretty happy with the whole situation. But it's probably not what you want. You'd also think at this point, Sam, people don't build systems like this. I can go through about 5 or 10 different case studies I dug up of payment services and systems where exactly this thing has actually happened around money being drained from people's accounts. So what do we do here? Well, this is where we introduce a concept called idempotency. And this is a mathematical concept which I do not understand because I'm bad at maths, but I think I'm good at common sense. And for me, there's a very basic kind of construct around, well, way of thinking about idempotent operations, right? An idempotent operation is an operation that you can apply multiple times without changing the result. So it's something we can safely retry. So in this situation here, this operation, as we've described it, is not fundamentally idempotent, because carrying out the same operation a second time should still only yield me being £100 up, but as we've got it modeled here, is actually going to result in me being £200 up. So we would say this operation is not fundamentally idempotent. So how do we make it idempotent? Well, there's the best way, which is most painful, and the less good way, which you might have to do if you can't retrofit it in. So we can look at request IDs, and we can look at server-side fingerprinting. Okay. And ideally, you want to do request IDs. Request IDs are actually really straightforward. It's a very, very simple idea. We're going to generate a unique ID for that request, and that's going to be used to identify a specific request. And this is going to allow a server to identify that it's seen that request before and ignore it. Very straightforward. So I pay Sam £100, but now we introduce the concept of a payment ID, 456. That first payment went through, but something went wrong with the response. I say, I really want that £100. I send it again, I send the ID along, and the payment service is like, sure, we've already paid that money, but yeah, it's done. Really, really simple, Lovely, easy to do. Don't confuse these with correlation IDs, right? Because a correlation ID is typically an ID used to correlate multiple calls together. This is a single request ID. So you do an ID for it. So if you've got like a chain of calls, you might have a correlation ID for the whole chain, but you would have a request ID for each individual piece. This also wouldn't be the same thing as a span ID in, say, using OpenTelemetry, because with OpenTelemetry, you do track each individual call, so the span IDs actually change. So this is actually a different thing to all of those. Right. Really, really simple ID. The problem with this is really straightforward. You have to change the client-server protocol for this to work. The client has to send the request ID, and the server has to respect it. So this makes building a protocol where operations can easily be made idempotent quite easy if you think about it up front, which is lovely if you have a time machine. But if you're discovering this stuff today and you're like, but Sam, I've got a complex system which we don't have putting request IDs in, and yes, we can start putting them in, but that's going to take a long time, or we've got legacy software that doesn't behave in this way, well, then what can you do? And that's where we look at the other piece of this, which is server-side fingerprinting. And this is where, on the server side, when we get that request, we're going to generate effectively a fingerprint of that request. And then when requests come in, we check their fingerprint and see if we've already processed them before. This is kind of the only game in town, really, for idempotency if you have no ability to change that client-server protocol. And in rare situations, you would actually use both of these things together. Like the AWS APIs use both of these things together, which, if you have time, I'll talk about why. So if you think about a request I'm sending here, so a simple payment request I'm sending, and I can see the fields, the customer ID, a payment amount, and then, so I've got the header and the body. And again, the concepts of headers and bodies are kind of HTTP-specific concepts, but this could be a message, right? It's the metadata in the body of the payload, right? And so I would take the body, generate a hash. This is an MD5 hash. So I could say, well, the request ID is that was processed, and I could write that to a database, right? The payment nodes could say, that's been done. I write that out to a database, so I know that's been handled. A second request comes in, it matches, we're good to go. The issue with the server-side ID, with server-side fingerprinting, is there are lots of corner cases that make it a bit difficult. And in certain situations, make it really tricky. Depends a lot on the nature of your API and or the interaction, how you expect it to be used. But I'll run you through a few kind of pitfalls around server-side fingerprinting, which is why I don't think it's what you want to do if you can avoid it. The first is kind of what I would almost consider to be client errors. So in this example here, we've got a protocol where we have a timestamp of when the request was generated, and the way this client-server protocol has been designed, that timestamp is put in the request. So when I do a retry, the timestamp changes. So if I'm generating an MD5 hash of both of the request bodies here, those MD5 hashes don't match. Right? So that's a problem. They are the same request, it's just the timestamp's changed, but the hash looks the same. So a couple of ways to solve this. The first way to solve this is to say what we're going to do is effectively mask off part of the body. So we're only going to look at certain fields in the body. That gets a little bit tricky, right? Because when new fields are added, do they need to be accounted for or not? Do you go for a kind of a whitelisting approach, a blacklisting approach? So that's not ideal. But again, often, if you're using this approach because you're retrofitting it into a system you can't easily change. So some kind of masking might be needed. Now, of course, the ideal approach here is to say, well, what is that timestamp? It's really a piece of metadata. That should actually move up into the header, and that's conceptually the right place for it to live. However, if we can make a change like that, we can change the client and the server, and if we can change the client and the server, just use request IDs. So just something to bear in mind. And this is a fairly nicely structured payload, right? Again, legacy software, it isn't always like this. It could just be some JSON blob monstrosity with no schema, and you've got no idea what's going on inside that. And in those situations, you'll normally need some kind of exclusion. And so that gets a bit tricky. And again, often when you're worrying about idempotency, it tends to be for operations that are quite important, and so getting these things wrong is not ideal. There are other issues here let's consider a situation where you love my work so much, you want to send me £100 every week. So you pay me £100. This is like the worst kind of NLP. This stuff is supposed to be like much more subtle than this. I don't have a Patreon, don't worry, right? I should get a Patreon. So here's the MD5 hash for this operation. Great. Time passes. A week later, you think, you need to pay someone another £100, still like his stuff. And I go to send it again, but the hash is the same. Because fundamentally, you're paying me £100. The hash is identical. So in this scenario, we say, well, actually, now what we probably want to do is have an MD5 hash, a fingerprint that's maybe only kept for a certain period of time. Maybe we keep it for a week, or a day, or an hour, or a minute. And exactly how long you keep that for might depend a bit on your business. But now we're starting to get into some of those grey areas, right, which is just not ideal. But probably want to do this, right? But then what about a scenario where you really do want to do the same thing multiple times in a short space of time? A good example would be spinning up VMs. So I'm going to spin up a VM, and I want to spin up 5 of those VMs. I might do that in a for loop. So I'm calling, I don't know, the AWS APIs, the Azure APIs, and in a for loop, saying doing the same thing 5 times. And the requests look identical. I'm doing it in a very short space of time, and it's completely valid. Now, again, the Azure APIs and the AWS APIs require request IDs, so they know that each of those is different calls. But you sometimes do get scenarios where you do want to do that in the same period of time. So again, there's all these nasty corner cases around server-side fingerprinting. I think it's also valid, by the way, this is talking more generally, you do get sort of client-type errors with these situations where even with request IDs, someone sends a request, and then they retry the request, but they do change the body. I actually think it's valid for you to error at that point if you want to. I think it's a little bit up for grabs, but I would argue that if you're retrying an operation with the same request ID, but you're changing the body, that you actually error at that point. The AWS APIs do that. And they do that partly to educate the user, right? You shouldn't be doing this. Now, for you to actually have done that, it means you're not using their APIs, you're not using their SDKs, you're going straight to the underlying APIs. But that's something for you to consider inside an organization where you might say, look, when you do the retries, don't change anything. And you may still want to do some server-side fingerprinting to pick up the fact that the body did change, so you can then report back an error. Or maybe you still carry it, you say, look, the operation you asked, because in that situation, it's like, what do I respond with? So if I sent the first request to you, and you did that first request, and I processed it for you, great, but you didn't get the response. And you then retry it with the same request ID, but now you've changed the body. What response am I supposed to give? Because I did the first operation, not the second. So it gets very confusing. So typically, you might do server-side fingerprinting on this, even if you can do request IDs, purely to pick up those kind of bad client behaviors. I won't say it's going as far as in an environment where you've got untrusted clients, but certainly this is why AWS and Azure do this, because effectively anyone outside your company has to be considered to be untrusted in this sense. But it's also, I'd see, it's about educating the users of your services as well. So again, this is a kind of an open question. I think it's got a very straightforward answer. When you do retry an operation that previously had worked, what response should you give? Well, the answer is you should give the same response that you tried to give the first time. I gave you a response the first time, you didn't get it. And nothing is happening here. So I'm just going to give you the same response again. So that's the answer, right? So when you do a retry, and you're retrying something that had actually worked, and the server has identified that we already did that, you ideally want to give back exactly the same response, semantically. Yes, it worked, no, it didn't. If the first one didn't work, the retry doesn't work either. Right? Because you got it, you tried processing it, and you couldn't. Then you start having to deal with what error codes you retry and which you don't, which is, again, a conversation. I could do a whole conversation about HTTP status codes, but nobody wants that, I've been told. So, in this example, I say the payment ID, I sent it was an accepted, but you didn't get that for some reason. You do it again, I send back the same accepted header, the same accepted response. Now, bear in mind, when you send that second response back, the semantics is it worked, I'm letting you know it worked. You can still be free to have some information that's varied in there. For example, I could put some information in the header to say, like, the body's the same, it worked. But in the header, you can say, This is the 15th time I've told you about this, and I'd wish you'd stop asking, right? You can still put things like that in it. Semantically, the response is exactly the same, right? So, timeouts, retries, idempotency. Idempotency, tricky. It's actually simple if you can just change the client-server protocol. If you can, request IDs are going to make your life so easy. If you go and have a look around all sort of the public-facing APIs for companies like Stripe and Square and AWS and Azure and all these people, they all have request IDs for any operations that are rights for this reason. You should put those things in as well. It doesn't just apply for HTTP-based communication. It absolutely applies to anything over message brokers as well. Request IDs are very much a thing you should do. They're easy to put in and easy to handle. Retrofitting them is difficult. With legacy software or software you can't easily change, do consider server-side fingerprinting. In many situations, it might be absolutely fine. Just do be aware of the downsides of doing that. So doing the same thing over and over again may be really sensible, but only if you can do it safely. You don't want to start draining people's bank accounts. Speaking of doing the same thing over and over again, here's that Einstein quote, wasn't it? The definition of insanity is doing the same thing over and over again and expecting a different result. Only he didn't say it. The thing we keep doing is saying Einstein said this quote. He didn't. There's no evidence he ever said that quote. So maybe that's the definition of insanity, is us saying he said a thing he never said. In this day and age of us hearing facts that apparently are made up, I think it's important to do your homework and check who said what. Einstein's never said that, and he's not around to defend himself. And it's kind of a fun quote and useful, but actually in the context of distributed systems, it's really bad advice. Right? The best advice is doing the same thing over and over again might be a good idea until it's not. But that's not as catchy, right, is it? So in summary, sometimes you should give up. Timeouts are completely and utterly appropriate to find a balance between keeping users happy and keeping the system stable. You likely already have the ability to specify all the timeouts you need just by using the software you're already using. The question is, do you know what those timeouts are? Start, I would suggest, by just looking at those histograms if you can get them for your services. At least start off by getting them kind of for the user-facing endpoints. Start understanding what they're showing you, double-checking them. The problem is often you only know timeouts are wrong when you start getting in issues like the ones I talked about before. And that might be a bad time to find out about it. Retrying absolutely can make sense to a point. So think about how many retries you want to make and the gaps you want to leave between them. And remember, that's going to be an overarching timeout for something else blocking coming in. I would strongly suggest using a decent connection library like Poly, like Resilience4j. Those things also have some really useful add-ons to these kind of concepts. You can look at things like token bucket and leaky bucket connections for things where basically it's a different way of doing rate limiting. It's really useful. Those are advanced things. Just get your timeouts and your retry policies right first. They give you the mechanics to do it. And all that they can do is give you default behavior. They don't know what your application is doing. So understand them. Right. If you do want to retry, which you probably do, you really need to make sure that your operations are idempotent. And if you can do that from the beginning, request IDs make your life easy. That's kind of all I've got. If you click on this thing, there's a QR code. You can get the slides. You can also, if you go over to my website, you can sign up to my mailing list. I do like a mail once a month, which is just stuff I found that's interesting. I also share bits of my research for the book and the progress of the book as well. The latest chapter on the book is now available in early access. It's on talking about thundering herds. So you've already got chapters up there available on timeouts, retries, and idempotency, rate limiting. So I talk about load shedding, back pressure, circuit breakers, a whole lot of different types of kind of ways in which systems fall over under load. If you don't want to sign up for an O'Reilly account to read that book in early access, you can get like a 30-day free trial and watch it and read the book then. Right, it's fine. But thank you so much indeed for all your time. Now, we do have time for some questions. Anyone got a question for me? anyone? Question at the back there. I'm an old man, so if you could come forward a little bit, it might make it easier for me to hear. I've already, I feel bad now because I've made you walk up here to come and watch the talk, and now making you walk even further forward.
So, you said that under certain circumstances, it could be more advantageous to have both fingerprinting and request ID.
Yeah.
But if I understand correctly, request IDs are supposed to be fairly foolproof, right?
So the scenario where you'd want both is in a situation where you can't 100% trust the client. So if the client does a retry, but changes the parameters of the request. So they say, here's request ID 4, I want you to do this. And then they say, I still want you to do request ID 4, but I've now changed the parameters. In that situation, you get into a confused world. So the client shouldn't do that, right? If I said pay Sam £100, and then when I'd retry it, I keep the same request ID, but I now say pay Sam £1,000, I might think you've paid £100 and you paid £1,000 or vice versa based on the response. So a reason to do both on the server side is in a situation where you don't fully trust the client and you want to be very clear about what's actually happened. So the situation where the first request ID 4, pay £100, I processed that and paid £100. You then, on the client, retried the operation but changed the parameter. The response comes through, said, yes, that was paid. Did I pay £100 or did I pay £1,000? That's the reason we might do both. I think it's a little bit niche, but I think it's something worth considering. And I think where it is useful is in a situation where you're trying to educate developers about what they should and shouldn't be doing.
So this should only be the case where you don't have full control over both client and server.
Yeah, and I would say in most microservice architectures where I work, that's the case, because often your service, think of it as it's basically a defense mechanism to an extent, but like a lot of times in the organizations I work, I'm managing 4 or 5 services, and I've got teams over here using my services. I don't control their code. So if that code's coming from another team, I think it could be useful to do. I would definitely put it in the nice to have category, and I think it's a conversation that you should have. But like if you're putting these things in now, I would have a conversation with your clients. Here's what we're going to be doing. Here's how it's going to handle. By the way, when you do a retry, don't change the parameters. And then you can say, and we'll be looking. Right? We'll send out a naughty list. So I think it's a bit niche, but I think it's in a situation, like if your team is doing the client and the server bit, don't worry about it. It's in a situation where somebody else is writing the client, consider it.
Thank you.
You're welcome. Hang on. As a gift to you for walking forward, I have books to give away. There you go. If you don't want it, you can give it to a well-meaning person. There we go. Thank you. All right. Anyone else got a question for me? Go ahead.
I totally understand the standard on using the request ID.
Yeah.
But just to understand the standard around HTTP, there's an idempotency key header that's been defined. What do you think?
I think if you're using
request ID or
I think if you're using HTTP at that level, by all means use that standard. The issue is lots of people use HTTP but aren't using it directly. So if you're using HTTP directly, use it. Now do bear in mind that idempotency key, there's a lot of public examples of the request IDs out there that predate that because that was added to specification later. But if you're using HTTP directly, use that. But a lot of you might be using gRPC, for example, in which case that's hidden from you. Always, 99% of the time, do what HTTP says. Like nearly always, it's doing the right thing. Book. You get a book as well. Everyone gets a book. All right, any other questions for me? Question in the back there. You've got a microphone. We've got an assistant. Thank you so much.
Cheers.
Go ahead.
So if you're going to do request IDs and fingerprinting, and you don't get the response in the first one, so for the retries, you were saying send the same response. So if it succeeded the first time and you retry, you give back the same response. Would you check for that the body hasn't changed and maybe give a bad request or something?
That for me is a bit of ambiguity. So I would argue that that's actually an error state. And it's a confusing error to give to a client. The first thing you wanted to do, I did. The last thing you asked me to do, that was trash and I haven't done it. It is a confused error. But I think probably the right thing to do is kind of to error, to say you kind of stuffed up here. The HTTP protocol does not give us a status code for this. Yeah. So this is where you would have to probably come up with your own variation within that And it would be a 400 series, so you'd pick one of the 400 series errors to put in there. I could probably pick one of them that's close. But yeah, I really think, strictly speaking, it is an error. Because again, if I don't give you an error, from a client point of view, which one of those two things actually worked? And I think it's better that the client blows up in that situation.
Yeah.
Book.
Cheers.
You get a book. All right, there we go. Thank you. We've got any other questions? Thanks. Any other questions? All right, well, you've been fabulous because you walked up here. You're already fabulous when you walked in. But thank you so much for your attention and your and everything else, and for getting up here. Thank you for coming to NDC. It's a great conference. I hope to see you again around here later today and tomorrow. If you're interested in security and security education, please do go and see my friend Laura Bell, who's running the SayStack booth downstairs, literally underneath this as well, because she's awesome and so is their content. And lots of other great speakers to watch tonight. Go watch Kevin's talk later. I think he's going to be talking about some of this stuff. Anyway, love you all. Have fun. Stay safe. And I'll see you next time.